welcome to our presentation on object recognition using traditional machine learning technique. This project, we explored various models including KNN, SVM, NaiveBayes, RandomForest, CNN, MultilayerPerceptrons, and gradient boosting. We followed key steps such as loading the CIFAR dataset, pre-processing the data, training and testing the models, followed by detailed observations and analysis. In the pre-processing stage, the data's pixel values are normalized between 0 and 1 and the class labels are converted into one-hot vectors, preparing the data for effective training.
We used KNN for object recognition on the CIFAR dataset. After normalizing and flattening images, we applied KNN with k-value 7 using Manhattan distance. Since KNN classifies based on neighbors, there is no real training phase. We got 37.64% accuracy. The confusion matrix shows a lot of misclassifications, especially among similar looking classes like cats, dogs, and birds, which highlights that KNN struggles with high dimensional data like CIFAR.
The NaiveBayes implementation with PCA-reduced features on CIFAR is a simple, fast, probabilistic classifier that assumes feature independence. Despite this, it achieved 32.75% accuracy and an F1 score of 0.32. Class 4 deer had the highest recall of 55%, while bird performed worst at just 6%. The confusion matrix shows heavy misclassification between visually similar classes like cat and dog or truck and automobile. While it's a decent baseline, NaiveBayes struggles with complex image features, suggesting the need for CNNs or more advanced models.
We used gradient boosting on CIFAR with PCA reducing dimensions to 150 for faster training. Gradient boosting builds models sequentially, each correcting the last. There are 3 hyperparameters in gradient boosting. Through hyperparameters tuning, we found the best accuracy at 250 estimators, learning rate 0.1, and max depth around 4. Our accuracy improved from 38 to 43%. We got some experimental results on how the accuracy changes with 3 different hyperparameters as shown in these graphs. Confusion matrix analysis shows good classification for classes like frog, sheep, and truck, while high confusion was observed between similar classes like cat and dog.
We implemented a multi-layer perceptron with 2 hidden layers of 128 and 64 neurons using ReLU and Adam Optimizer. Images were flattened and normalized. We achieved a test accuracy of 48.97%, but the model didn't fully converge in 100 iterations. The training curve showed stable learning while validation accuracy slightly fluctuated across folds. From the confusion matrix, we saw strong performance on horse, frog, and truck, but frequent confusion between cat and dog, bird and deer, and truck and automobile, highlighting MLP's struggle with complex and similar looking classes.
We tested RandomForest with different feature types and tree counts. Starting with raw pixels, accuracy rose from 36.1% with 10 trees to 49% with 500, but gains slowed after 200, showing diminishing returns. Switching to HOG features, improved accuracy to 50.6%, highlighting the benefit of handcrafted features. Finally, we used deep features from efficient NetBayes to capture rich visual patterns and then reduce them with PCA to manage dimensionality. This combination gave the best accuracy of 51.5%, outperforming raw and HOG features.
The model first flattens and normalizes the data to reduce dimensionality. We use PCA and reduce it to 100 principal components. Support vector classifier is then trained on this dataset. The model achieves accuracy of 51.5%. Confusion matrix is generated to analyze class-wise performance. We observe that predictions are balanced. This shows that model is not biased, but accuracy is low due to dataset's complexity.
The CNN model uses 2 convolutional layers with max pooling and dropout to extract features and reduce overfitting. The features are flattened and passed through a dense layer before final classification with softmax. It was trained for 20 epochs using Adam Optimizer and categorical cross entropy, with 20% of the data used for validation. Training accuracy reached about 88% and validation peaked at 78%, showing strong learning. There's only a small gap between 2 curves, meaning overfitting was minimal. The final test accuracy of 77.44% confirms that the model generalizes so well to new data.
We tested several machine learning methods on CIFAR from NaiveBayes and KNN to RandomForest, SVM, and gradient boosting. While traditional methods offer decent performance, they rely heavily on manual feature extraction and struggle with complex visual patterns. In contrast, CNNs automatically learn spatial features from images and achieve the highest accuracy overall. So for image classification tasks like CIFAR, CNNs clearly stand out as the most effective and reliable choice.